Well, good evening, everybody. Who would imagine that all these people would turn out in Perth on a Friday evening for a talk on quantum physics? We're amazing, aren't we? But if any of you are worried that this might go over your head, I'm sorry. No, I'm not. Ross is well briefed, he totally understands. So this will be a talk about quantum without too much of the quantum. Okay. So, a wee bit of background. I just learned that Ross is from Perth and went to Perth Academy. Yay! Now his dad used to run a pub on Princes Street, and he used to work there when he was a wee laddie, and he hasn't had a haircut since. Correct?
That's all correct.
All correct. So we're off to a good start. So tonight, you've seen all this stuff. You know the next one. So I'm not going to talk about the PSNS stuff. We'll just get straight into Ross and his little story. So, Heriot-Watt University. He did his degree there, did his PhD there, and now he works there. But he's got a really nice position there. He's kind of, well, I don't know, I haven't spoken to him about it, but my impression is that he's almost a kind of self-employed researcher there. You've got Royal Society of Engineering Fellowship, I understand, that basically pays the bills.
That's right.
Yeah, so you don't really have to work to get your pay.
Just a little bit.
Just a little bit. Just a couple. Anyway, so he's been very successful at a relatively early stage in his career. He's got a 5-year fellowship that allows him to devote his entire time to his research. Now, when we first came across him, we came across him because we'd spoken to his PhD supervisor and said, "You got anybody interesting?" And I didn't realise this, but he basically said, well, Ross would do it, because Ross comes up to Perth anyway occasionally. So it'll be easy. So Ross was going to talk about the quantum internet. That's an interesting subject. We'll come to that in a minute. But as I was preparing to do this, to stand up here and to introduce him, I asked him for a little bit more information on himself. And he sent me a link to a blog that he participates in, or an interview thing. I'm not even sure what it was. And that was him talking a little bit about the space industry in Scotland. And I have to say, I didn't know there was a Scottish space industry. How many people here are fully aware that lots more. Okay, it's just me. Or is that because you read my email? Yeah. The Scottish space industry, I really didn't understand. So I began investigating it a little bit more. And my goodness, there really is a Scottish space industry. I was astonished to learn that some 10,000 people in Scotland are directly employed in the space business. What surprised me even more was that there are only 40,000 people employed in the Scottish whisky industry. So it's 25% of the size in terms of employment of the whisky industry. And it brought in something like £300 million worth of revenues last year. That's actually a big business. And it turns out that Scotland is the world's second largest manufacturer of satellites after California. How can that be? Well, we're going to hear a bit more about it tonight. So tonight I'm going to hand over to our guest now, who's going to tell us a little bit about his work and how it fits into the bigger picture of space research in Scotland.
Perfect. So the title I gave into this was using satellites to create a quantum internet. Before I get into what parts of that sentence mean, we'll give a brief introduction in highlighting what is going on in Scotland in terms of space, what we're trying to do at Heriot-Watt, then try to answer the critical question at the end: what is quantum? How how are we going to create a quantum internet, and how will that be of any use to anyone in this room? The best questions. I should also highlight, as well as being at Heriot-Watt University, I recently joined a company because we're trying to commercialize technologies that we're making in the lab called Luminal Technologies. They're a company that was based in London, and they're so impressed with what we do up at Heriot-Watt that they opened up a lab space and hired half of my team, which causes me some trouble because now I have half the team for twice the projects. I'm not sure what to do there, but we need more people. I see there's young people in the audience. Do physics, do quantum science, and then come join my team. There we go. The career's already sorted. So briefly touching on the biography again, I always find when people talk about their what they've done through school, through university, it's always very positive, all the awards they've won, all the great things that they did. When I was at Perth Academy, I was probably, what would you say, Alison, middle of the line student. A slight nod. So you probably, I wasn't causing trouble, but I'd always be part of the trouble in some way. But I had an ambition to become a nuclear engineer. I was very interested in how you could generate power using nuclear particles. And that's kind of what motivated me to do very well in science, but not so well in quite a lot of the other subjects. That kind of set me on to Heriot-Watt University. I did want to do nuclear engineering as a full-on degree, but the only place in the UK that ran that was Lancaster University. But at the time, I think it was 2008, I had to pay £3,000 a year to go to university, and I was like, oh, that sounds a bit steep. 4 years later, it was much more expensive. But I chose to do engineering physics, so a lot more applied things. So stuff that I cover in quantum, particle physics, nuclear physics, I actually did a lot more of engineering, electrical power grids, how we actually take nuclear power, generate it, and then put it onto the grid to give us electricity. So very, very applied stuff, and not as mathsy as a lot of other physics students at the time, which I was quite happy for. During that time, I was actually signed up for a master's, but unusually I left my degree at BSc level and joined an academic supervisor for a PhD in quantum technology. So quite a swing from nuclear engineering to quantum technology. And the push for that was in 2012, you may remember, there was a tsunami, which caused quite a lot of trouble in Japan, in nuclear power plants. That then led to a global kind of wavering on nuclear energy. So I thought, why would I graduate and go into a sector that's probably going to collapse in the next 10 years? I'll do something with a bit more footing with it, quantum technology, which I've never heard about before. Seemed like the best thing to do. But luckily, I think with a lot of my career, a lot of us to do with timing and basically just jumping onto opportunities that came up at the time. So I joined Heriot-Watt as a postgrad researcher for a couple of years. Got involved in a couple of critical projects, and again, the timing will be very relevant later on in the talk. And then I ended up with a research fellowship because people were very interested in doing quantum technology in space, and I said, so am I, but I want to do it on the ground. And that's why we're building telescope systems. And because everyone was very interested in the space side of things, that kind of the research sector for that, how much grant money you would put into that sector, kind of dried up. And what I said was, well, this company I've been speaking to that works with BT say when they put one satellite up, they need 10,000 ground stations to actually do a commercial service. So it's costing you £20 million to build a satellite, but it's costing you hundreds of millions of pounds to develop the ground segment. So that's actually what the problem is in the commercial challenge. So I based my research on trying to solve that problem, and that's where Luminal Technology comes in as a commercial exploitation partner. But again, same with my other academic careers. You know, there's not a lot of awards jumping out at me, but I still managed to do very well in getting research money to do really interesting work. So you don't always need to be in the headlines to have a very successful research career, which I think a lot of people forget about as well. So starting at a very high level, there was a report released by the Scottish Science Advisory Council in 2024, which kind of captured what was happening in Scotland in space and what we needed to do in order to maximise what we were doing. So just a boring table to start with, it highlighted some strengths, weaknesses, opportunities and threats to kind of work out what strategy was. So actually we do, as was pointed out, we do a lot of manufacturing of satellites in Scotland. We're not talking about big satellites, we're talking about this new generation of satellites which are based on essentially shoebox size systems. So this is the satellites that Elon Musk and others are launching to create a telecommunications service. These are not systems that cost hundreds of millions of pounds, these are systems that cost tens or 20,000s of pounds to put together and then cost you 800,000 pounds to put to space. But he doesn't want his own business, so that's fine. And then they provide your telecommunications service for there. So that's how we can then put up thousands of these satellites at a time very quickly, rather than manufacturing satellites that take typically 10 or 20 years to go through a cycle. You launch one satellite with technology that you were working with ages ago. So this allows us to do things much, much quicker. There's lots of other strengths. Weaknesses, a traditional space presence. So this was where we have big companies looking to essentially squash new space. So rather than having systems that you can pull, essentially like Lego bricks and put together, they were saying, oh, well, these systems will only work in this specific orbit. We won't be able to put them out into geostationary orbit, which is what we're trying to do now. The opportunities are obviously to do with commercializing, so we hired thousands of jobs. We could probably double or triple that if we bring more students into undergraduate degrees that are focusing on space. But the big threat is for us, especially as a small country, is internationally and particularly in Europe, where newer countries bringing in new money and new funding are essentially bringing in a new generation of engineers and companies are being tempted to move their headquarters back into Europe out of Scotland. And another thing that continues to be a problem is things like infrastructure and regulations. So people who have tried to get a building permit from the council or tried to do any big projects will know all the steps you need to take. When you try to launch something into space, that's magnified a millionfold and can cause quite a lot of delays. And these delays mean people can catch up on you and can also overshadow what you're doing, which is what happened down in Cornwall with the delays there and are currently happening with the spaceport in Shetland. Just to highlight it's not just the central belt of Scotland, but there's actually things going across the whole map of Scotland as well. So I mentioned there's the Shetland Islands, Sacks of Origin, you may have heard that in the news quite recently about them building a spaceport there. They're definitely the closest now in the UK to launching something. There's 4 other spaceports competing with them. Sutherland Spaceport in the top of Scotland. There's also Machrihanish, which is a horizontal, so there's different types of space vehicles that people are looking to launch. Most people will think that vertical is the only way to go, but horizontal has some environmentally friendly, if you can call space things in the space environmentally friendly, benefits. But there's also lots of other companies around the country. There's places at Tayside. I noticed that point there, I'd say, is more in Perth rather than Dundee. But all those companies are based in Dundee. Different universities as well. Most people, when they think of universities doing space, they think of Glasgow, Edinburgh, Strathclyde. But there's lots of other places doing things nowadays. And big companies. But most of this is involved in new space. So again, thinking about these shoebox-sized satellites, creating components that go into them and making those scalable, such that you can make thousands of them, so that we can launch those satellites quickly. But there are other companies. You think guys like Elon Musk have got the satellite launch market completely saturated. There's 4 companies based in Edinburgh who are doing their own launch vehicles and own propulsion. And again, they have different benefits over what's being used at the moment, which makes them really interesting. And again, just pointing out, why is space moving so fast and developing so fast nowadays? That's literally a satellite you can hold in your hand. And it weighs very little as well. The components that are made up for this, communications, computers, other types of boards, solar panels, antennas, these are all small parts that can be pulled together. Again, this is like a Lego equivalent of a satellite. Typically what you find is the only thing that's different is one component for these satellites. And that's kind of what everyone is relying on is to get their stuff into space. It used to take years to get space qualified components. Now you can pay less than £1 million to put a vehicle like this into space. It goes around for 2 years. You show that your component still works. Hit the box, it's space qualified. I've saved myself £20 million of development. So it's a very quick way of doing it. just to give you a size, is so nano satellites are typically what people are launching nowadays, with micro becoming as you want to test more things and more complex stuff. Mini satellites are kind of becoming a hybrid between these Lego brick satellites and bespoke stuff. And then you get into this kind of sciencey satellites where it really is teams are spending 10, 20 years putting these things together. Maybe a bit faster nowadays with all the money that ESA and that put into things. So that's what we're doing on a national level. What are we doing at Heriot-Watt itself? So I guess Heriot-Watt, when I talk to people, they always think of Heriot-Watt being more about oil and gas or other types of engineering, not to do with space engineering. And to kind of combat that, I was working in space, and I knew a couple of other academics who were. So we organised something called a Space Cluster Workshop. We invited companies we were working with and different academics together to kind of understand what the landscape of research was like at Heriot-Watt. It turns out there was 35 people in the whole of the Edinburgh campus who was working in space. So that was myself, who works in telescopes, but also people in a place called the Lyell Centre who are working with Earth observation data and using that to track how fish farms were operating and moving and the environmental impact of them. So quite different things, but actually a lot of the data that they use is very high in resolution, and you can actually use the technology I work with to increase the amount of data transferred over. Sometimes it would take them weeks to download their data, and we could offer a technology that could do that in less than 20 minutes. So these kind of bringing together just different people, understanding what the technology requirements are, is quite interesting. We also released a new aerospace degree 2 years ago, which seems to be demolishing the physics degree. There's only 40 people in the physics degree, and now there's 80 people in the aerospace degree. I think someone told me about aerospace engineering basically being applied physics. So all those people who were doing engineering physics are now doing aerospace engineering. And I was like, I probably would do aerospace engineering if I was offered it. Based on that success, we have a new MSc coming out, which will attract some more funding, more students from the EU and abroad. And they created 5 academics for that as well. A professor came in from the Netherlands who worked with cyclists in the national cycle team in the Netherlands, essentially doing wind tunnel measurements. And the first paper he released when he came to Heriot-Watt was to do with why people with curly hair run slower. And I'm like, I always knew there was a reason. I always needed the excuse. So again, it's always really interesting finding what other people do. And we have a big research part on the campus as well. And the idea is we're trying to get some money to build a building or buildings to host incubator space for spinner companies and small companies to then manufacture stuff on site. If you want to find out some more, there is something called the Space Academy website, which captures all of these different activities as well. So just to highlight them in a little detail, of those 35 academics, we tended to find about 25 of them working in these 4 core areas. So radio communications is how we do things nowadays. This is what Elon Musk's technology, at least satellite to ground, is relying on. So there still is research in this area for antennas in space and how we get those signals from space into our phones. Optical and quantum communications, so that's the area that I work in with a couple of other academics. Space robotics, so it's quite funny how this theme came around. We hired a couple of academics from Bristol University who worked on robotics, and they worked in underwater environments. And the way they pitched themselves as being related to space, as they said, well, we were looking to put these robots in one of Jupiter or Saturn's moon, which apparently has some ice we could turn into water. So I was like, that's a very nifty way of getting yourself a job, which is quite nice. And then something else that I always forget about this topic is called position, navigation, and timing. Where would we be without GPS and the timing in our phone? I wouldn't be here, although I do know how to get from Edinburgh to Perth, so that's that. But this is a critical technology, for everything, logistics. It's something I always forget about, but it's very important and something we're looking into as well. Building space, so engineering into applied space, it needs facilities. So one of the 3 things we're proudest of. One of them still isn't here yet, which is the wind tunnel. And the idea is we want to bring a wind tunnel in to do some experiments. We have a flight simulator that the engineers brought in. Again, part of the contractor coming in, they said, I want this flight simulator. And I was like, surely that's just a computer with a keyboard and a nice seat and a big screen. But apparently the software on it is not Microsoft Simulator, Flight Simulator or something. You can actually load in engineered models of planes to actually test how they would fly in practice using some very sophisticated software. So it's much more advanced than I thought, apparently. We have a telescope down here, which I'll talk a bit more later as well. So it's bringing these critical infrastructures in so that students can use them, so that when the students go into the real world, they actually have practice of using these things, which is what people really want. There's always this complaint about, or the feedback we had from students is, when the student graduates, they have some skills. When they go into a company, the company wants them to have different skills, so they spend a year retraining them in something different. So you're like, why did they go to university in the first place? It's almost a waste of money. So we're trying to bridge that gap by making sure we have equivalent facilities in the university as you would be using out in industry. Another big thing we're doing as well is supporting student successes. So lots of student societies exist now. Something called CANSAT. How many of the students heard of CANSAT? Tell your teacher to look into it. It's a UK space agency, an ESA initiative. So essentially you get given, it's not really the size of a can, it's maybe two cokes of can on top of each other. A tube where you need to fit in electronics to measure altitude, speed. You need to fit in a parachute and the propulsion, so it shoots out the parachute such that the vehicle can land itself. And there's competition over in the US every year where they launch your they launch your can into the air up to a certain altitude, and your can has to pop out of the rocket, launch the parachute and land safely, and you have to be able to go find it after. So it's quite a fun thing for the students, but you think all of these skills that they learn are actually really useful in everyday engineering. Another one is the Rocketry Society, so they basically just build the rockets to just go really, really, really far. And that's what they have to measure. There's other students from physics who do something called What's Up. So their aim was to battle at the time the growing flat earthers. So they were going to put a camera on there, launch it up into space, and take a photo of the curvature of the Earth and show that off. And then there's recently a WhatSat team who have started, who are going to design a CubeSat, and we're going to find some funding to help launch that CubeSat into space as well. So lots going on. And in terms of our external engagement, we want industry to be involved with what we're doing. We hosted something called the Parallel Summit, which is an organisation focused on space sustainability. So we're already talking about being sustainable in space, as well as being sustainable on Earth, because we're making a mess of things already. And the idea was, theoretically, we can fit 2.9 million satellites into low Earth orbit. Should we do that? How can we manage that? And how can we actually make ourselves, what should we actually do it? So we hosted a few industry workshops around that, and also fed in what we were doing with courses, and got some feedback into industry. And it turns out companies who work in space want students to know how to space qualify something. There you go, that makes sense. But a lot of space programs in the UK don't. And this is also features the UK Space Agency and Scottish Enterprise, who have a big influence on exploitation of space technologies. So what does this have to do with the initial topic, which is about using satellites to create a quantum internet? So I think at this point we've still got a few questions to answer. So first one is, what is quantum and why is it useful? What is the quantum internet? And again, why is that useful? And why do we have to do it using satellites? Why can't we use the fibre optic internet that we're using today for all of our communications? And finally, how will this impact you or me? Depending on which way we're going to look at it. Essentially, the taxpayer who's funding all this research, and for me to be here today. So I'll take a sip of water actually before I jump into the rest of it. Before we move on, does anyone have any questions on the space sector side?
If you want to ask questions at this point, yeah, please go ahead. Yes.
Why do you need a wind tunnel for space research? It is a vacuum.
That's good. The program is called aerospace. So that's the thing that was, when I think about aerospace program, the first thing in my mind is satellites. But there still is a big need for aeronautical engineering as part of the program too. And that's always the fighting point when it comes to traditional degrees versus new degrees, is aeronautics played a lot in traditional degrees. And traditional universities are afraid to move away from just having a satellite program. It is something we've been trying to get Heriot-Watt to do, is listen to industry that says, if you want this to be an aerospace and satellite program, you don't need the wind tunnel. And you need to have facilities there that do space testing, vibration testing, radiation testing. So yeah, it's a very good point. And it also comes down to the academics you hire as well. So if you have a facility that's not going to be used for research, it's going to cost the university money. It's easier to have an academic who's in charge of it, who will bring in research money to run it for you. And you still need to get them into space as well. So there still is some aerospace engineering needed.
Sorry.
Yeah, carry on. Yeah.
Wind tunnel costs about 20 million for a copper tunnel. Are you using the tunnels down south near Formula 1 businesses?
So the Formula student. Yeah, so
Did you hear that question?
Yeah.
No, wind tunnels were really expensive. Okay, I think you said 20 million pounds.
For
Yeah. And there are some very good ones down south, I believe, for Formula 1 applications. Is that right? And yeah, so why have your own one when you can use
their facilities.
Red Bull's one?
So this is exactly the same why we've made a new telescope facility when there's other telescope facilities around the UK. So they're already a capacity of use. So it means by expanding them out, everyone becomes cheaper. It also means we can control it as well. So it's like a local need. So there is a lot of talk about collaboration and using facilities around, but at some point everyone's using the same facility, so it just becomes impossible to get time and become quite restricted. But yes, £20 million is quite big. So this is where ideas about a new building on campus are central around what facilities we want to put in there.
So we'll have plenty of time for questions at the end, but Ross just suggested having a wee break so he can get his brain in order for the quantum stuff. Yes?
You spoke about several spaceports, and they're all up north. But given the fact that if you're putting something to orbit, it needs to have multiple axes of movement. The original reason for putting NASA in Florida was because that gives you the best centrifugal force to get for the speed, so you need less fuel. So surely going north makes it less efficient. So why are all the spaceports really far north and not as far south, on islands, in the Mediterranean, or even, further south near the equator?
Yeah.
I gotta say, to someone who knows nothing about the subject, that's a good question.
So I'll see how I answer then.
Yeah.
So I guess it depends on what type of orbit you're looking into. Low Earth orbit space is typically around the central belt, the equator style. In fact, we hear people talking about these grids of constellations of satellites going over the top. You don't see them that regularly in Scotland, but if you move down into Spain or further south, you see them a lot more regularly because that's where their orbital band is. A lot of the interest is moving into primarily polar orbits. So those are orbits that go right across the top of the globe and from pole to pole. So that's where some of the advantages from having this high latitude. And again, there is a defence reason for that as well.
Is that also the reason that Svalbard is covered in satellite communication dishes, because of its location? It gives it a better view of these
high latitudes, yeah. So definitely these off-axis lower Earth orbit ones that are going towards the polar. If you have ground stations at higher latitudes, you can see the satellites for a bit longer. Which is why when we talk about our ground station again, people are like, well, why would you have a ground station in Scotland and Edinburgh when you could put it in Tenerife? where the European Space Optical Communication Telescope is. They say, well, I don't want to go to Tenerife. Well, that's not an excuse. But the point is, it's opening up you place something in a difficult place where other people want to be, and then other people will come to you to do things. So yeah, it's to do with the specific orbits people want to go in from up here.
Right, one last question and then we'll get on to the quantum stuff. Yes?
There are many countries putting satellites up into space and into orbit of the Earth. Who decides, if you want, you might be wanting to put yours up, but so does everybody else, and as you said, you can put 2.9 million in low Earth orbit. We've already heard people saying there's an awful lot of space junk out there. How can you fit it in, and who decides who can have the space to put their satellites in?
Well, who figures out who gets what space in space?
Yes, again, an interesting one, and that was the real aim of the Neparo Space Summit, was to understand the international regulations around that. And really the idea is, if you're up there first, you're up there first. And so this is a big problem in space, especially from the Americans' point of view, is they used to be the biggest space player. And now other countries, because we have these small sats, are catching up very quickly and launching many more per day, like China, Russia. The UK is seen as a space player, but can quickly fall behind if we don't start launching things. The spaceports help a lot with that, because it's a sovereign supply. And it means we don't need to ship things to Florida. Kazakhstan, I think, is another popular place to have things launched. I'll mention it now, but I'll probably bring it up later. The CubeSat that we're launching as part of our research program, there was only 4 slots this year we could launch it. And you have to submit your satellite to that program with launch 6 months before. And I'm going to say, anyway, we're delayed until next year, and that means we're 6 months delayed just because of the launch. So that, again, depending on what orbit you're interested in going into, there's some restrictions, and hopefully with these new spaceports, it helps reduce those restrictions. But again, it is basically, there's no control at the moment. It's really up to companies to be good actors, which is not a good place to be. And again, we are trying to, the government is trying to bring in regulations and policies around it. Some successful ones have been around CubeSats, and the CubeSats have a lifetime. They're in low Earth orbit, so eventually, not gravity, there is some air up 100 kilometers. It's very, very thin, but there is some resistance of that satellite over time, such that if it takes 7 years, it'll naturally deorbit. But some of your space systems might stop working by then, and what happens if you need to move out of the way of something else that's going up? So there's now a thing in place where you need to deorbit your systems before they stop working. And so that means the satellite we're launching, we paid for 3 years extended lifetime. Sounds like buying a car. But that means all the systems that are on board have a 90% chance of working after 3 years. And it means after that point, we have to deorbit. Even if everything's still working, we've reached the end of, things become too high risk beyond that point. So we, as our organisation, have chosen to deorbit at that point. And that's what's being, and that's another reason why we're launching so many satellites, and the lifetime intervals become shorter. So previously they thought 7 to 10 years, it'll naturally deorbit. Right, so the first question, what's quantum and why is it useful? If you type quantum mechanics into generative AI, it gives you this nice diagram. And I have to say, I was actually quite impressed. It does remind me of quantum mechanics. So you have your atomic structure in the middle, and it's not actually a quantum mechanical structure, it's the wrong way to draw it. It has something like a wave, reminds me of the wave function that everyone talks about in quantum mechanics. You've got some Hamiltonian equations written several times because they can't find any other equations to put in there. So yeah, it kind of reminds me of quantum mechanics. Generative AI is done well there. And also when people are introduced to quantum mechanics, they're often hit by some back in the day, the big physicists, the quotes. So Niels Bohr, who won one of the Nobel Prizes, if you aren't confused by quantum mechanics, you haven't really understood it. Okay, should we stop? God doesn't play with dice. That was one of Albert Einstein's, because he didn't like quantum mechanics. So Albert Einstein doesn't like quantum mechanics, why should we? And finally, from Richard Feynman, a popular American physicist, if you think you understand quantum mechanics, you haven't understood quantum mechanics. Again, okay, maybe we should just skip these slides. So when I first looked into studying physics, this was even 10 years ago, these phrases, these quotes were still banded around quite a lot. And to me, who was someone who was getting into learning quantum mechanics, I always thought this is a bit of academic snobbery. You know, they're in their white tower, they've done their equations, they don't want other people to learn what they're doing. Of course, 10 years ago, or 15 years ago, the government decided we want to commercialize quantum technology. And what does that mean? It means people who are academics now need to tell people in industry how to make their technology such that they can commercialize it. And that means engineers need to understand what your technology does. So I then said, these are very dated quotes. 60 years ago, that might have been correct because this was very, very academic. But we already have technology based on quantum mechanics, and we are now creating a new generation of technologies based on quantum mechanics. So how can we build technologies if we don't understand what we're doing? Doesn't make sense. So luckily over the past 5 years I've seen a lot of people move away from these types of quotes, trying to be a bit more inclusive. Of course you can understand quantum mechanics, everyone can understand quantum mechanics, and that's what I'm going to try to do here today. Maybe. So where did it all start from? So I guess, again, Albert Einstein was well known for not liking quantum mechanics, but it's his fault we have quantum mechanics in part. So he won his Nobel Prize not for general relativity, which a lot more people known for doing, but it's discovering something called the photoelectric effect. And this was an experiment where he had a gold leaf on a metallic surface that could be charged. When you charged up the surface, the gold leaf bounced off to the side, or elevated because there's charge in there. When he shone red light on the surface, no matter how high intensity he put on it, the gold leaf wouldn't move. However, when he moved to a different wavelength, in this case it suggested it was the UV, the gold leaf slowly went down, and as he increased the intensity, it moved faster. And basically what he discovered is that there are discrete energy levels. All the light that we have around us is made up of particles with discrete energy within them. And this also comes into something to do with atomic structure, where we have absorption and emission lines, which gives us spectroscopy, or different colors of light from molecules, and we call these discretized energy levels quanta, because there's no energy in between them. You either have that energy or you don't. There's no in between. And this is why that gold leaf flattens down, is because those UV energy have enough to kick the electrons out and decharge the metal plate, whereas the red ones, no matter how many you put on, individually they don't have enough energy to kick those photons off, so it remains charged. And so this is really where the first wave of quantum technology came from, these discretized energy levels. So we term these quantum technology generation 1, and surprise, you may not know it, these are things you use all day. And I'm using one now. So lasers and LEDs that use semiconductors, these are based on discretized energy levels. That's quantum technology. Atomic clocks, which rely on energized energy levels and those falling off in different transitions, those are based on quantum technology. Electronics, your phone, semiconductors, quantum technology. And MRI scanners and other medical devices also use discretized energy levels. So there we go. We're all using quantum technology today without knowing about it. But that's great. So these have been developed for the past 1950s, 60s, maybe some go a bit further back. But you think about all the money that has been generated from things just like electronics, just from understanding that there's discretized energy levels if you put two materials together. So what happens if we take an entirely new generation of quantum mechanics that we've discovered over the past 30 years and try to create new technologies from those? And that's what essentially has driven something called generation 2 quantum technology. So these are things that are maybe not, we don't use them every day, which is why we think they're counterintuitive. So we have something called a qubit, rather than a classical logical bit, which is essentially a superposition or entanglement particle which you can use for sharing information. And the mechanics that we use are something called quantum entanglement and quantum superposition. Entanglement, some of you may remember or may have heard of Einstein's spooky action at a distance. This is where he didn't believe that if you separated these two particles that were entangled to the other side of the universes, that if you measured one, you instantaneously knew what this other one could be. And essentially what you have to do is measure one, run to that other one, measure it, and then verify. But quantum mechanics tells us you don't need to verify, because if they're entangled, if you measured this one, you already know what this one should be. And he just didn't like that at all. And of course, most people have heard of Schrodinger's cat, where if you put a cat in a box with a radioactive element, you don't know whether the cat has passed away or not until you open the box, which I think is always a very sad one to do. But based on these two phenomena, we can actually use those to encode qubits such that they have this thing they call superposition, where you have your information is either in the 0 or 1 position. Until you measure it, you don't know whether it's a logical bit 0 or 1. You can build computers based on this technology such that you have this entanglement. They go through some processes, and then you get some information at the end. And because it's been an algorithm based on quantum mechanics, which is a different form of mathematics to classical mechanics, you get possibly ways of answering different questions faster. And so what my career is based on is how do we share this quantum information and verify that it works. And so this, unfortunately, is a bit more technical. But we have a little break after again, just to make sure we all understand quantum mechanics, so we can go back and cross off those quotes. So I call it light quantum. So when people call me a quantum technologist, I say, yes, but I'm the light version of quantum. It's not because I work with lasers, and it's a pun on light. It just means it's a lot easier, hopefully, to understand and actually implement. So we have light, which is a single particle. It can be encoded in different ways. So light has polarization, which means its electric wave is either going this way, if it's vertical, or horizontally that way. It can actually go in many, many, many different ways, but for now we can just say it can only go in 2 different directions. This means, like with classical information, if we know we have a horizontal photon or a vertical photon, we can say it's either a bit 0 or a bit 1. So we have our bit values. To measure that, we have a special optic, which is called a polarization beam splitter, which allows us to fully distinguish between the horizontal and vertical photons. So if we receive any photons, if we measure light at the top detector, we know it was vertically polarized. If we receive a click at our detector down in the bottom, we know it was horizontally polarized. And we count this as our measurement 1. What happens if we then rotate those photons by 45 degrees? So it's no longer horizontal and vertical, they're slightly off, but we can still distinguish them fully. However, we need to make a special measurement instead, because if we still use measurement 1, our polarization beam splitter actually splits this 50-50. So it means if we're looking at our detectors, actually 50% of the time we're getting a measurement we're completely wrong. But we don't know what the initial value was, because this is supposed to be the thing that allows us to distinguish. We can fix that by putting a reorientator in front of our polarization beam splitter, such that it allows us to fully distinguish the horizontal and vertical. Those 2 cross polarizations have been realigned such that they're horizontal and vertical, allowing us to remap the initial encoding. So we have 2 ways to encode data, 2 ways to decode data. There we go. So we have our classical sets of data for each of the various encoding sets. And what we actually send out into our communication channel is a superposition of all these 4 different states. Because we only have one photon, we can only ever make one measurement. It's not like classical data where we could have lots of these measurements stacked together and statistically we'd be able to figure out what it is. If you only have one photon and you use either measurement 1 or measurement 2, you won't actually know what the actual encoding is unless you get some additional information that tells you which one of these was the right measurement to make. So what we've done is carelessly included some uncertainty in our communication, such that if someone doesn't have an extra bit of information, they're not able to actually work out what's going on. And that causes confusion, well, it causes confusion all the time, but it causes errors in the system, such that if you have an eavesdropper who is performing an intercept and resend attack, that means someone standing between us, who's measuring all the information that's sent, and then anything they measure, they have to pass on to me in order for me to measure it as well. It means they essentially have a 25% chance to get the wrong bit passed on. So this way we essentially have a secure encryption key sharing by introducing some uncertainty into things. And it's all because we have multiple sets that we're encoding in with multiple states, and we can't fully distinguish any of these 4 states on these 2 measurements without knowing one bit of information, which one of these is the right one to make. And so that long, drawn-out way is a way of sharing information. I should say the whole point of it is to be secure rather than high bandwidth, which makes sense because you have to do a lot of processes after and before it. But essentially it's based on the fact that we have 4 states that we need one of these measurements to make, but one of these measurements might be wrong. What's the point in that in the first place? This is something called a quantum computer. It's another quantum technology. This is a superconducting qubit, one from Google over in California. It's believed that a universal quantum computer, so that's something that behaves like the computer you have at home, not like some of the quantum computers that exist today already, with a sufficient number of qubits, so that's the bits that you process, like the RAM in your computer, with a low error rate, because these things have very high errors, could run specific algorithms to decrypt encryption algorithms that we use today. So think about when you're sending an email, it has the padlock in the corner that tells you your encryption, your message is encrypted. That could be stored, and then a quantum computer could be used to break that encryption to read the message. And just to highlight the 2 algorithms that could be used, is one called Shor's algorithm and one called Grover's algorithm. And these have time benefits and process benefits over a conventional computer doing the same problem. So today we use encryption mainly, which is based on the fact that it's difficult to defactorize a problem. So you multiply 2 prime numbers together and you get a really, 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 really big number. It's very difficult without knowing one of these 2 prime numbers to guess what the 2 prime numbers are, and it takes a long time. For the type of encryption we use today, it's said that that should take a supercomputer that Edinburgh University has 1,000 years to figure out. It's said that a quantum computer, in the way I've described it, would take less than 12 minutes. So the way we think about encryption is completely different with capable quantum computers out there running certain algorithms. And Shor's algorithm allows you to factorize faster, and Grover's algorithm allows you to search things faster, so to go through databases faster than before. And so the process I described to you before, where we have two ways to encode data, the 2 different sets and the 2 different measurements, is essentially a process called quantum key distribution, where you want to share an encryption key using superposition. So you have Alice and Bob. Alice sends those encoded bits to Bob, either in set 1 or set 2. They don't tell Bob yet. Bob has to make a measurement between set 1 or set 2. 50% of the time they're going to guess the wrong measurement. So where does that help him? Well, it helps him, as in we have an eavesdropper in the system, they'll also have a 50% chance of guessing the wrong measurement. So they're both at the worst positions at the moment. Then we do something that takes away that quantum uncertainty. Alice actually reveals to Bob which of the measurement sets they should have measured in. So when Alice sends in set 1, says, did you measure in set 1 or set 2? I measured in set 2. Okay, we'll get rid of that information, that's wrong. Okay, well, this other one I measured in set 1, or well, I also encoded the measurement set 1, so you keep that bit of information. So you get rid of this quantum superposition, at least for the two people who need it, through doing this reveal of information with the two measurement sets. And this eavesdropper doesn't have access to that, which means they can be identified in the channel. We do a measurement called the quantum to error rate measurement, which essentially takes 5% of the information that you've shared and you reveal it publicly and compare against each other. And if you go above a certain threshold, in this case, the attack I've described about measurement and resend would be 25%. If that error rate goes to 25%, you know for a fact that that eavesdropper's in there performing that simple attack. So you've revealed the eavesdropper, you can get rid of your encryption key that you've shared before you even shared any private before you've even shared the email that you plan to send, and you can try to regenerate a key another way. There's other processes on top of this for anyone's interested. Error correction codes and privilege amplification. They're for computer scientists. So actually, there's a very small part of this is quantum. The rest of it is using conventional information. So this is why it becomes more about sharing information securely rather than doing something quickly, because it's going to take a long time to do all that other processing as well. So when it comes to quantum superposition, this is something that I do for a job. How do we actually generate these states? So I've called them sleds. I'll point them out on there. So these are typically lasers, but in this experiment we used a different type of semiconductor called a SLED, superluminescent diode. No one's ever heard of these things. But they've got some interesting properties. They're like a hybrid between a laser and an LED, so they give you a broad spectrum, but they have a gain medium, so they have some good spectral properties. It's not very interesting for anyone. But you have 4 of these put together. You use certain optics to essentially combine them, the different polarizations together, and what you have is then your superposition state that comes out of here, which goes into your communication channel. And we then build receiver systems that then look at that as well. And in between the two systems, we then do our post-processing as well. So quite a lot of stuff. But for me and a lot of other people, it's typically quite hardware intensive. As well as to encode these things, you also need something called a quantum random number generator, another quantum technology on top of that. So it becomes quite hardware intensive. If you want to set up a system, you need a transmitter to receiver, which does some management of the encryption key, which then transmits and receives again. So there's lots of different processes in there. And the way people actually want to do this in the future, particularly Americans, is to use something called quantum entanglement instead. So this is where you have a laser that comes into a crystal with some special properties. It allows it to generate pairs of photons that are entangled. And what we mean by that is if your photon up here is vertically polarized, you know your photon down here is horizontally polarized, and vice versa. If this is vertically polarized, you know that one is horizontally polarized. And you need a much simpler system to generate these, and the receiver system is essentially the same. But basically you're looking for correlations and statistics between that. And so that's essentially the way the future way we want to generate these bits and share things. And why are they useful? Well, actually the main use is for something called distributed quantum computing. So it's envisioned that quantum computers are going to be quite infrastructure intensive, I think is the polite word, such that you would not have lots of these in the same area. You might have 1 or 2 of these in a nation, and if you want to then use your combined computing power, you would do something called distributed quantum computing, where you try to link these all together to do bigger problems, which seems completely impossible with today's geopolitics, but we'll see. So the idea is that why we want to do quantum networking is to use entangled states to link these quantum computers together. There's also very valuable sensors as well that you can use to connect into these two. And we'll take our second pause there. If you want to get some questions.
Come on then, surprise us. Yes, I knew Colin would think of something, yes.
Do these work at room temperature, or do they have to be super cooled to?
The quantum computers, typically they're cryogenically cooled. Again, there's different technologies that people can use to make these qubits and quantum computers. A very popular one seems to be based on superconducting junctions, which is actually what the Nobel Prize was for last week. Their discovery of Josephson junctions and using Josephson junctions as qubit states. There's actually a company that came out of the UK in Bristol called sci-comms, set up in California, is now valued at more than £1 billion. Investment from the Australian government, and they also have investment from the UK, DSTL, which is based on photonics. So think of your electronic circuit, and they've developed a photonic circuit which does all the processing. The issue with that is the superconducting ones can be reconfigured quite easily. These photonic ones, once you write the circuit, your algorithm, that's it. You can just do that one thing. So if you want to solve different problems, you need to have all of these different circuits in there. And again, the detectors for those are superconducting because they need to be high performance, so it also needs to be cooled. So yeah, most things seem to be going towards superconducting. Room temperature is everyone's dream, but I don't think it'll happen.
Yes.
One of the problems with AI is a massive increase in energy consumption. What's quantum going to do? Increase energy consumptions or decrease it?
Did you hear that question? Yeah. AI uses a boatload of electricity. So these quantum computers, do they kind of just sit there using, can you plug them into your house socket, or do you need a nuclear reactor to get power of the thing? Yeah, essentially? Yeah.
Probably somewhere in between.
So they are energy hungry.
Energy hungry.
Yes.
I mean, the cryostats, you need typically liquid nitrogen and compressors to keep that going. But you have a lot of amplifiers and stuff. So once it's done its process, you need to transfer that quantum information to something we can understand, which is typically amplifying it. So we have lots of different signal generators that then transfer that onto a computer that we then get out. So yeah, they're pretty intensive on power as well, I would say. Maybe not so much because there's only going to be so few of them, but still it's going to be bigger than your PC at home.
A bit like computers, we're only going to need 2. Is that right?
That's now you've got 1, 2, 3.
Yes. But just so, oh yeah, okay.
Sorry,
You first, go on.
Just a
Yeah.
quick one. So I'm trying to understand your structure there. So you have your data in space being transmitted to a source, I would imagine, on the ground using a quantum stream. And then I know already the satellite communication level is far higher than fiber optics. That's a huge fiber optic network. That's massive.
Yep, and not only that is the next bit is telling you we're not going to use the fiber optic network because we can't.
Yeah.
Because we'll get on to the problem next.
Right. So can I clarify something? Yeah. So there was a question about the quantum computers, but for the stuff that you're doing, okay, you showed these SLED things, and you're basically doing this quantum encryption. Is that right?
That's mainly what I do. Yeah.
That's what you do.
Yeah.
The quantum encryption, but that doesn't require a quantum computer.
No. So the aim of the quantum encryption is to, if someone has a quantum computer, it takes away the threat that they'd use that to break your encryption.
So the quantum computer is the baddies out there trying to break your encryption, and you are making this incredibly cunning, way of encrypting your messages so that even a quantum computer can't.
That's the idea. Yeah.
Yes.
That's the research. But actually, I did a talk at the Fringe a few years ago, which actually pitched it the complete opposite way, which was we were the bad guys looking to protect all of our information about attacks, etc., what capability we had, and there was the good guys with the quantum computer who were trying to break our encryption. So they say, it's that fun, which way you pitch the technology.
I don't think any good guys have quantum computers. That sounds to me definitely like the sort of thing that the Bond villains would have.
Yeah, but it's funny with these things as well. So we talk about the encryption breaking when you tell the general public, oh, your information could be broken in 12 days or 12 hours. You're like, well, is that really what we'd use the quantum computer for, breaking someone in this room's privacy? I'm not sure. We'd probably use it for more difficult problems first. Because again, these are big infrastructure projects. There's going to be so few of them. The impact on probably day-to-day in terms of breaking encryption wouldn't be so much.
Yeah.
But it's the fact that also other computers are still able to break encryption today.
Yeah.
And it isn't just quantum computers that can break encryption. It's just that they've got such a significant step change between them.
Now, if you had a quantum computer, you would want to mine Bitcoin, wouldn't you? Something useful.
That's yeah. So I think there was a paper last week from what would the impact of quantum computing be on Bitcoin. And stuff. I didn't read it, because I think it was written by someone who's invested in Bitcoin. So it's obviously pitched for them.
Okay.
One more, just there.
Yeah.
You said it was very technology intensive,
Mm.
and obviously if you're working with stuff with very short wavelengths, are you not every time the temperature changes a bit, are you not just effectively with all those mergers, are you not just ending up with so much sort of constructive and destructive interference that you're losing all your data to practicalities and temperature change and everything else?
Yeah, it's a really good point. So that's one of the challenges is quantum decoherence is the problem you're talking about. So as you scale things up, temperature changes between lasers can change the wavelengths. Interferometers for doing measurements, if you change the temperature on anywhere, they can change, as you say, constructive, destructive interference. So this is where this company, sci-comms, comes in, and the idea was to scale everything from lab-based experiments down to photonic integrated circuits. So this is the next wave of where we're going with technology. And there was a huge investment from the UK government in a facility in Cardiff, which is looking at semiconductors and photonic integrated circuits and trying to keep the UK, I'm not going to say in the lead here because they're quite far behind Europe, but competitive. But there's people working on those things as well.
Good. Okay, time to move on. See, I warned you there would be some interesting questions, didn't I?
The challenging ones as well.
Yeah.
So this gets to the final part, which is towards the quantum internet. So how are we going about creating it? I think the important thing to start with is actually reflecting back on how our internet was created and it works today. And really the backbone structure of our internet is highlighted in the top right-hand side diagram. Depending which way I was going, which is optical networking, optical fiber networking. So these are deep subsea cables that run all around the globe, allowing us to connect Perth, Australia to Perth, Scotland, through these cables. And really, for the past 20, even 30 years, this has been the structure of the internet. And it's only recently that we've seen this emergence of satellite networks growing, doing radio frequency from satellites to the ground, using low Earth orbits constellations, and that's guys like Elon Musk with is it Starlink?
Yeah.
Starlink, and then there's the UK OneWeb. Or has that died? I can't keep up with the technology there. But the idea was our fiber optic network is great, but it can't reach nomadic platforms. Think of people on oil rigs, people out at sea, or people traveling through the desert. You can't take a fiber optic with you, not at the moment. So the idea was to provide high bandwidth communication to those directly from satellites. Actually going to space, even though you're going 100 kilometers up into space, it's actually lower latency. Even though you're traveling at the speed of light, if you're going through subsea cables, the material is slower, so the speed of light is slower, but also there's lots of networking systems, amplifiers, transceivers that measure and then resend your signal. So actually going through these systems is particularly slow, especially if you want to do something very quickly. An interesting side story that I was told recently, In the US, I think back in the early 2000s, there was a fiber optic network that went from Chicago to New York, and some investors created a shorter cable such that they had something like 100 milliseconds of advantage over the stock exchange than other people in the world. Quite interesting. So lower latency is really, really important for a lot of applications. And at the moment, people think it's harder to disrupt satellites in orbit. Although some of the news we hear recently about Russian satellites circling our own satellites, it's a bit disturbing. And we'll see how things go. I should also mention optical fiber networking. There is another technology being developed in the UK and around the world called hollow core optical fibers. So these are things that have essentially air rather than glass in the middle of them, such that they are lower latency than the glass fibers. So they're a technology to listen out for in the future. But yeah, so the idea is there's this emergence of a growing network in satellites, and people want to go from radio frequency to optical communication to take that bandwidth from tens of megahertz up into tens of terahertz. So thousands of a fold increase. How do we do that, and what's different? So that looks like the top of someone's house with the various different sky dishes. That's what you need to do radio frequency communications. I think the Starlink one costs you £500 deposit to do it. So our spectrum is completely different. We're not on the radio frequency, we're now down where lasers work in the visible and near infrared. When we look at satellites, so geostationary satellites that should give us our Sky TV, or used to give us our Sky TV through radio frequency. It's great that the radio frequency is very divergent, so it covers a very big area. If you want to do secure data transmission, you want that area to be much smaller. So rather than 1 kilometer cell, you want something to be like 10 meters. However, that means you need to have very, very high precision when it comes to pointing and tracking, especially when you're trying to point to something that's 10 meters from hundreds of kilometers away. And the sensitivity is also different, especially when it comes to quantum. We're measuring single photons, and we can't amplify any of our signals. So whatever we send out, we need to be able to receive. And this unfortunately means our infrastructure needs to be a bit bigger than what's needed for optical communications. And you can see there's a clear difference in the type of hardware we need. So typically the telescopes that we use have big mirrors on the bottom of them, costing £20,000, £30,000. That's clearly not scalable, and it's something we're working on to reduce. But clearly the technologies are different, and that's why people like me are here to research that and make it better. But what are the challenges with moving to the optical spectrum? So it turns out that most of the time when you have a cloudy day, you won't be able to do laser communications to space. Why, again, are we setting up a telescope in Scotland to try to do the experiments? Is to basically understand how we can overcome those challenges. So one of those is to actually move to different wavelengths that are slightly longer, but the detectors don't work as well, and then that drives research to make those detectors better, and then we overcome that. That's the whole process. It turns out for quantum communications as well, the sun is a big problem. Not as big a problem in Scotland, but we still have it occasionally. And also ambient light. So think about light pollution. If you're in the middle of a city and you look up, your horizon has basically got a lot of light pollution haze around it. That causes a problem for quantum communications. As we heard about before, decoherence. So making sure our particles are still entangled when they reach the places they're supposed to be. And there are other problems because we're sending single photons, because we're sending entangled photons in superposition states, we can't amplify them because it breaks quantum mechanics. And each operator, if they were able to clone it, means they'd be able to get that information and resend it with 100% accuracy, which they can't do. So how do we actually create a quantum internet? Well, it turns out the easiest way to do it is to start with the satellites in orbit, because that gives you a constellation of platforms to then transmit down to the ground. And then on the ground, have a local supporting metropolitan network, which is less than 100 kilometers in length. And the reason for that is if we go to optical fibers, we have to amplify every 100 kilometers. We can't do that. So the best way to scale it globally is to just have a satellite in orbit that allows you to go to different places and downlink data to different locations. So that's why we're exploring satellites, and that's really the aim. Another reason for not using the fibre optic network around the globe for quantum as well, it's based on, again, geopolitics. If we want to go through a certain area, we want to go through the shortest distance. That might be through an area that's not, I think, what was the term they used? An area of disruption, and someone could cut your cables. That happens quite regularly to normal optical communications and electrical cables in the North Sea. Imagine if we're trying to manage that across the other side of the globe. It's much easier to do it with a satellite. It is quicker to launch a satellite into space than to create a network between here and Australia. There we go. So where are we globally? Not a picture. It's a picture of a satellite and then put together with AI. This is a real satellite in orbit. It's called Mucius. It was the first quantum-capable satellite launched into orbit. And the first Western satellite is still to be launched. So we're quite far behind. Well, so what have they done? So they have shared entangled pairs and superposition states between ground stations in China and also a ground station in Austria, Graz. Conveniently, they've also done an experiment with Moscow in Russia and also South Africa and also some other states. Clearly avoiding the US, the UK, and other European states as well. But it's been very successful. You see it on the bottom right-hand side here. It's left-hand side. It's a 600 kilogram satellite with two large telescopes, 30 centimeter and 25 centimeter, to point at different locations on the ground. The second satellite that they've launched is called Jinan-1, which was launched in 2022. They took the payload size from 100 kilograms down to 10 kilograms. By doing something very similar to what we're doing in the labs at Heriot-Watt. And you can see, it's quite different in size, but their bandwidth capability was from megahertz up to 10 gigahertz, so quite a substantial change in pace there. And they also have another one they're planning to put in geostationary orbit in 3 years' time, which is apparently the size of a bus. Which is quite interesting. So they're very capable. As well as that, the Chinese also have a 2,600 kilometer optical fiber link between Beijing and Shanghai. So they're very capable. Really, when it comes to technology development, it's more about money. You just throw lots of money, and then people will come and do it for you. What we're doing in Europe, one of the big missions is called Eagle-1. As you can see by the UK being slightly greyed out, we're not involved in that mission, but we know a lot of players who are involved in it. The idea is to create a European quantum access infrastructure with ground stations in different countries that then link onto metropolitan style networks as well. Other ones, there was an initiative called T-Quants, which was funded to Thales Alenia Space. And they've been recently funded by SAGA, which is one of the ESA programs, to launch a satellite in 2027. Again, the UK is included in that one, but the idea is doing, you can tell by the two lasers coming out, it's the entangled pairs they're generating down, so they're already moving to the next generation of satellites for entanglement distribution. A Spanish company called Hispasat are launching something into geostationary orbit in 2 years' time. One of my ex-PhD students works there, and he told me it's going to happen in 4 years' time because they're still behind. But that's a really ambitious mission. It's going to be a huge satellite, and they're using ground stations in Tenerife to do their downlinking. In the UK, I'll bring both of these up. There's a company in Glasgow called Craft Prospect who won an ESA Vault, which essentially is a program by ESA which allows them to have a certain platform size to put their communication system on. As well as doing quantum communications, they're also doing a range of AI, LiDAR, Earth observation things as well, so ticking all the boxes that you need to, which is launching next year. No, it's not next year, that's 2027. And hopefully Heriot-Watt is going to be involved in downlinking the laser communications from their satellite. Had a value of just under 20 million euros, and has been led by a Scottish team, primarily with UK contractors. So this is a big win for us. An even bigger win is from Honeywell. So I think some people have seen Honeywell have like an office near Glasgow on the motorway. They also have a very, very small office, which is just outside Edinburgh Newbridge. You can buy a car near there. That's what I knew it for. But they do a lot of radio frequency stuff, antenna building, and they had one person who was working on optics with the Canadian team. And this guy has basically expanded out this team. He helped win this over €100 million contract for something called QKDSat. Again, two satellites looking down. It's about sharing entanglement. But it was originally led by a company called Arcit in London. They did the satellite mission QKDSat, but as a side project, they also did some software to do with encryption. That software started to make money, so the company divested the satellite engineers and the quantum team, and also the QKDSat mission, and Honeywell picked it up. So it's likely this one-man team from Edinburgh is going to grow to about 50 people over the next year, and they're going to be running this €100 million project. And downlinking to Edinburgh, Heriot-Watt, and also to BT Industrial Park. So Scotland, I think bang for buck, is one of the biggest leaders in satellite-based quantum communications in the world, just because of the teams that are here. These aren't research teams, these are engineers doing this project, so really cool. The rest of the world, again, Honeywell are involved. They have a mission called KeySat, which is launching next year. It's kind of a more scientific focused one. It is paired with the University of Waterloo, and myself and another academic are involved with taking some measurements to uplink data to their satellites. So rather than downlinking, there's also ways to uplink data and then also follow on with networking to different places. There's other stuff going on in the US and other places in the world, but I think the ones I've highlighted are the most fun for me. Aside from our own satellite mission. So in 2018, the Quantum Communication Hub was funded with a work package to launch a CubeSat. The idea of this CubeSat was it was supposed to be academic teams developing the quantum payloads that went on it. It would then be launched, and then a UK team would then build a ground station to receive the data as the satellite went over. The launch was supposed to be 2025, October, but as I said, there's how the launches work. We didn't meet a deadline, so we were pushed by 6 months into March next year. This is a 12U CubeSat, so think rather than just two shoe boxes on top of each other. So the next time you go to Clark's, buy two sets of shoes, put them on, and go. That's what it looks like. It's in a very polar low Earth orbit, so it could potentially be launched from one of our Scottish facilities. And the idea is it will pass across our Heriot-Watt ground station twice a day, most of the time inconveniently when the sun's out, so we won't be able to look at it, but we'll be able to track it with a telescope. The quantum payloads are being developed by University of York and University of Bristol. They have their own flavours of the quantum that they're doing, but the idea is this would be the first mission that has two different styles of quantum transmitter on it. The ground station itself is my pet project. So the idea was when we got the money for it, we wanted to have, the vision was to do something more than what we required for the mission, so design something that had a long lifetime to it. There we go. So that's what it looks like at the moment. We have a large telescope inside the dome there. We have something called adaptive optics. Is there any keen astronomers here?
Tim,
Of course. So he'll know what adaptive optics is. When you look up at the stars, they twinkle. That's not very good when you want to do imaging or take things into a fiber optic. So we have some fancy optics that tell us how it's twinkling and then tries to compensate for that, so it gives us a much clearer image and allows us to couple into fiber optic much more efficiently. We have a range of lasers and tracking sensors, and we're also looking to go into the mid-infrared and far-infrared to look like thermal imaging of satellites. So it means if a satellite is dead for whatever reason, it'll still be heated up by the sun, but it won't have any active cooling systems on it, so we'll be able to track it as it goes across the sky in different wavelengths. So opening up new different forms of space situational awareness, trying to help us overcome these problems with space sustainability. A lot of other functionality in there as well to be able to contact that satellite. Something else we also have on the campus is called dark fiber. An important part of doing communications is being able to communicate with other places. A lot of the telescopes that are being used for experiments are just a telescope, so you can't really do much else apart from that. If we really want to work in innovation and understand how we can network different things together, we need a fiber optic network locally to do that. So our ground station is connected to a large fiber optic network which connects us to labs to connect different technologies, potentially a small version of a quantum computer, but more likely different styles of detector, quantum memories, or different sensors. And this allows us to play around with things locally. It takes us 5 minutes to walk between buildings. People have already tried to scale these up to city sizes, but if you try to get from one side of London to the other, it's going to take you quite a long time. You walk from one side of the campus to the other, Heriot-Watt, it'll just take you 10 minutes, unless you run into another professor. So what we're looking to do beyond this first mission, so the mission is called SPOC, it's funded by the Comms Hub. We have another mission that we're working with, so that's the KeySat mission, which launches next year. QQDSat, when it launches in 2027. We have our local space Scottish cluster with different companies working there. We hope to take that fibre optic network and expand it across the central belt towards Stirling, Glasgow, Dundee as well, such that we can connect in different users, end users. We also are using the KeySat and QQDSat mission to talk to on a ground station at BT Industrial Park down in Ipswich. The idea is they have a lot of telecommunication companies down there who would like to interact with us up in Scotland, and we can do direct experiments between these two sites on the same day. That also connects into dark fibre infrastructure that connects into BT Tower in central London as well. So these are big national things we're looking to do. Locally, we're looking at alternative sensors, different wavelengths to overcome coming through clouds, quantum memories as well, so we can store information and then forward it on to different things. So ultimately, as a research team, the idea is we want to connect our devices globally using a satellite constellation network and a series of ground stations to do that. Of course, academically, that's quite difficult. Where you actually want things is commercialize things. So as I mentioned at the start, I'm working part-time with a company that's looking to do that. The drive of doing this with research money is UKRI, UK Research and Innovation. It's the people who fund this research. They say that for every £1 they spend on research and innovation through their programs, they get £3.40 back, which I think is pretty good concerning some of the people I know in research who just sit on it. I myself have one patent, which is a good celebration. I did have another one, but we got rid of it because it didn't seem commercially viable. And that's one of the things we're looking to exploit through Luminal Technologies. As well as that, we have some key partners, so that you'll recognise a lot of the companies that are up here. These are real companies who do real infrastructure and are interested in the technology that we're developing and taking it from the lab out into the real world. We've had lots of projects at BT, and now Vodafone is starting to get interested. The quantum key distribution system that I talked about, this is kind of the phase one of the infrastructure that they're planning. Everyone knows that the quantum networking is the real gold mine. But to go to that straight away would be too late. So they're building up their quantum infrastructure by basing it on quantum key distribution, doing a small investment there to build infrastructure that's capable of building a quantum network that's based on entanglement. So it's quite good to be used for the first phase. Toshiba as well, International Bahrain Honeywell, and also working with the Integrated Quantum Network Hub, which is why I was invited along here today to talk. So just a brief summary, just with pictures rather than words, because I know everyone's getting tired, and I'll start to lose my voice. Hopefully I've given you an appreciation of Scotland as a whole in terms of its contributions to the space sector, but also quantum. Heriot-Watt's contribution to that as well, through its undergraduate programs and its vision of being involved in innovation rather than just fundamental science. The threat of quantum technologies is real as well. All these technologies don't always come with the best intentions, and sometimes they're researched for naughty things. Also, we're a key part of the satellite networking at Heriot-Watt. And if you're ever interested to come down and see the facility, do get in touch with me. It's good to have visitors. to spend time not doing research. And just to highlight thank you to the organisers for inviting me to come along. And also, I do have a small team, but I'm part of a wider team that does detectors, LiDAR, and other single photon based technologies. But this is the core team here for now. So thank you very much.
Well, I don't know about you, but I thought that was pretty good. Have you got a question? We've got time for a few. Yes. Oh, the polymath David at the back. Yes. David.
I was thinking that, am I right in thinking that Scotland has certain special advantages in having quite a mix of useful resources, access to dark skies, reasonable security and safety, and access to clever people, and access to infrastructure?
So, did you all hear that question? Yeah. Scotland's advantages: dark skies, infrastructure, clever people. I agree with the clever people bit. And yeah. So, does Scotland have particular advantages here?
Yeah, for sure. In terms of the people, especially the universities. I think Scottish universities, bang for buck, we do very well, especially research funding, to get very highly qualified, very professional people here. And the elite teams, an academic puts out, is able to have about 10 PhD students. If each of those goes off to contribute to some of these companies, then it's only our benefit. The dark skies is good as long as you're outside of Edinburgh or Glasgow.
Mm-hmm. Yeah. Other questions? Yes, come on then.
In a worst case scenario, you could imagine Russia or China or Iran cutting a few of the internet cables by dragging their anchors. Elon Musk decided he's just going to switch Starlink off, as he did in Ukraine for a period. When can we get a satellite-based optical communications network up and running to protect us?
So, did you hear that question? So the question is, we're vulnerable because the Russians could cut our undersea cables. Elon Musk could just switch off his network like he did in Ukraine. When are we going to have our own fancy schmancy, unhackable quantum internet? McInternet.
Oh, that's true. If you let the Scots name it, that's what they'll do. So I think that the optical communication network in space will come faster. Already the satellites that do radio frequency downlink, they do space-to-space laser communications. Cloud Space, one of the companies in Glasgow that I mentioned, they already have a terminal that can do satellite to ground. It's just building up that constellation and having the sovereign supply to do it. I think there was a company, New Web, Space Web. There have been a few initiatives to start doing it, but they seem to fall under themselves due to lack of support. So I think it's probably going to be something the government has to prop up initially. Because even the constellations of satellite, they travel around, but they also travel with the Earth's spin as well. So it's not just a linear constellation you need. You do need quite large constellations. I think that's where the scalability of that struggles sometimes with sovereign supply. But I think they have the capability. It's just the big investment from the UK Space Agency. But I think that's a problem with lots of things.
Gordon.
Are you always going to be dependent to some extent on the weather and have downtime? Because okay, you can go to longer wavelengths, but you've again got the problem of water vapor in the atmosphere, which acts as a lens and diverges it. I feel you're always going to have some time, in fact, at which the communication is just the weather.
Yeah, that's right. So that's why there's skeptics about optical communication, especially when you come. They come as an Airbus, you do radio frequency communication there. As soon as you start talking about optical, they're like talking about the 5 nines. And I came from quantum communications, not a comms degree. So when I came to all these meetings and they were talking about the 5 nines, I was like, is anyone going to explain what that term is? Or am I going to have to look it up online? So it means 99.999, I might even be more nines, % of active service. And so that's what your network needs to have in terms of stability. So you're right, clouds, fog. We try longer wavelengths, but we get 995 rather than 999. It's not good enough. So this is where it comes in terms of distributed optical ground stations. So I mentioned the 2 that we have. The one we're working with, Heriot-Watt, and also Adastral Park. You're probably looking at having a distribution of ground stations around the UK, maybe even offshore, and connected by fibre, such that if you're not able to take data down in Edinburgh, you're able to take data somewhere else and then use a fibre to bring it home.
Or even a forest fire beside the ground station.
Yeah, exactly. And these are the challenges where I hope there's not a fire next to the ground station, but trying to overcome those challenges. It's going to be difficult. Sometimes you might have to sacrifice bandwidth for it as well.
Yep, the gentleman in the middle there.
That you spoke about how obviously the clouds and everything else. So you want it to be above the inversion in the atmosphere, but also dark. So why not have paired stations? Because they were elliptical orbits going up and down, so that you've got one as far north of the Arctic Circle as you can, and as far south as networks will allow, to try and maximise your uptime at high altitude locations.
So this is where the design for networks are really important.
Do you work in this field, or are you just a keen hobbyist? Yeah?
No, I'm an electrical engineer. So.
I kind of guessed. Yeah. Yeah.
So I guess that's why we said we're building one in Edinburgh. The first question you get asked is, what's the altitude? And then when you say it's 80 meters, and you're like, I hope you're away from at least the Har. We are away from the Har. The Har doesn't get to us at Heriot-Watt. But there's other challenges around there. But people have said, well, why building stuff on top of mountains, top of hills, cairngorms, things like that. And then it's about how the cost of getting that infrastructure up there. And then we have the other issue of the fibre optic networking. We have to get to there, and then the fibre optic down to somewhere useful as well. So costs are a big factor as well. Much easier radio frequency because you can still do the terrestrial link, point links as well.
Yep, the gentleman in the blue shirt up the back.
Yeah, you were also talking though about having to replace your satellites every 3 years. That's going to massive costs, even to get in. What do you have to get it up there in exactly the same spot, or can it be a little bit further away? Or
well, I mean, the interesting thing about satellites that I didn't appreciate, again, coming from somebody who worked in fibre before coming into this sector, is even now we get something called TLEs, they're called two-line elements to track satellites. That's based on radar information from stations around the globe. They don't measure them all the time, but you try to get them every 24 hours. If you get quite old data, say 48 hours, then it's likely the track you're trying to look at, your satellite could be off to the side by 10 or 20 kilometers or further away or further behind. So yeah, trying to get them in the exact position, it's not too important. Because it's naturally they're going to start drifting anyway, which is part of the problem with space sustainability too.
Okay, one last question. David,
Yes.
again, yes, come on then.
A slight vested interest. Given that optical communication is going to be important, optical frequency, is this going to make governments take dark skies seriously for the first time ever?
So did you hear that question? Given it's all about optical, is this going to make governments take dark sky seriously? Actually, it's a good question. I mean, how important is this dark sky thing? I mean, if you're...
Yeah, so it depends on what wavelengths we're looking at. So as you say, the optical spectrum, the visible spectrum, depending on what lights are out at the moment as well. So old school lights, tungsten lights outside, They have the visible spectrum, but they also have a large leakage into the infrared. And those lights cause us a problem for quantum communication in space, because the sources we use at the moment are at 850 nanometers. So if you have your TV remote, you point it at your phone camera, you should be able to see a signal coming out on your phone camera, but not with your eye. That laser or LEDs, it's just in the infrared, so it's just beyond what you can see. So yes, those causes problems. Also just for tracking satellites as well, especially if it's not illuminated by the sun. Sometimes you have optical beacons that come down to improve the signal to noise ratio. But if we start to talk about satellites that are using telecommunication wavelengths, which is the same wavelength that's used in optical fiber, which people are traditionally using now, probably not so much a concern for dark sky. However, I did a study a few years ago on light pollution. It was part of another fringe show in Edinburgh about having a light license, about being a bad outside light user. And a lot of the cars that are planned for the future, they have radar on them, but they also have LiDAR, which is the laser equivalent of radar. And they use lasers that are a similar wavelength to what we do in quantum, both in the infrared and also telecommunication wavelengths. And in fact, they can propagate much, much further. So that could be an issue for quantum in the future, technological-based light pollution. So yeah, but it would be hard to convince people in government. Here's something that you can't see that's a problem.
Okay. Well, yes, Gordon again, yeah.
From a military point of view, would there be a risk of jamming? Because it would seem to me, if you can locate where the satellite is, and you just have a wavelength, a laser of equivalent wavelength, you're going to cause problems.
Yeah. Right, so it's and your single photon at the transmitter as well. So yeah, one of my PhD students did a study on this, and they said it was based on another study from an Australian group, but I don't think they pitched it quite well. So they said kilowatt laser using a 40 centimeter diameter telescope could jam quantum communications. When you actually dived into the numbers in more detail, you could actually get a laser pointer that you could get online. And have a smaller telescope, something you could basically get for less than £200. As long as you could point accurately enough and track the satellite, you'd be able to have enough signal that it would be detrimental to the quantum communication transmission. So yeah, it's a huge problem. And then this is where we did a little study based on, well, this is the same problem that radio frequency band has. When Japanese or Korean satellites go across China, they get jammed. Because, well, natural. They're not flying across China where they're shining lots of RF frequencies at it. The same year, we looked at frequency hopping, so jumping to different frequencies, different wavelengths, encoding in different ways such that you could maximize your signal to noise ratio as well. So there was lots of techniques you could do to try to overcome it, but ultimately it's a single photon transmitter technology, so easy to jam.
Well, friends, there was a time some years ago when I was taught about qubits as a Babylonian unit of measurement, which I still use. And there was a time, again, some years ago, when I used to pass my evenings sitting on a bucket, rather like Ur Wally, with a telescope collecting photons from distant galaxies. And my main hardware problem was tears freezing on the eyepiece, because that's what happens in Montreal. Technology has moved on a bit since then, and I hope my understanding has moved on a little, but it's moved on a lot tonight. I have a strong suspicion that many of us have the feeling that the subject is getting ever so slightly ahead of us, but that's all right. That's what we wanted. And I think that we'll want to follow this closely, knowing that here in Scotland, we mustn't flatter ourselves, we're maybe not quite at the leading edge, but we're somewhere important, and it's going to be worth watching. And I rather hope that at some point in the future, we'll be able to drag Ross back here to tell us more about what's happened next. So for what he's told us this evening, let's express our thanks and appreciation. Thanks very much.